Okay. We'll be going over the XFLR5 project. So first off, you're going to want to go ahead and insert the airfoil that we're going to use. So I went ahead and grabbed it from the database. And I'm just going to pull it up real quick. I have it saved as the Clark Y. Go ahead and there's the Clark Y. I got the smooth one just to make things a little bit easier, a little bit more streamlined. So once that's in, we're going to go ahead and go to XFlow Direct Analysis. And let me see if I can. All right. And so what we're going to do is we're going to go ahead and define an analysis. And we're going to call this Clark Y. And according to the instructions, we have to do at a Reynolds number of 1,000. So I'll put RE. And then down here, we're going to change the value to, or I mean, 1,000,000, my bad, sorry. So we're going to go ahead and do 1,000,000. And then okay. We'll go ahead and move this to the side here. Sweet. And then we can go ahead and do a sequence of alphas or angle attacks. And according to the instructions, we're going to go from -5 degrees to 20 degrees at an increment of 1 degree. And then we go ahead and hit analyze. Everything converges, real nice. And we're given all the different graphs. So we can go ahead and look in a little bit more detail. So here we have the CL versus CD graph. Go ahead and cycle through. So CL versus alpha and CL over CD alpha. Also, we can define our graphs simply by right-clicking and then going to current graph, define graph settings, and we can change it to whatever it is we need. Based off the instructions, we do need CL versus alpha, which is CL versus alpha, CL over CD versus alpha, and then CL versus CD. And to go ahead and extract these, we go ahead and go to current graph, right click, current graph, export graph. Now being in the where we can see all the graphs, I will take all the data. So if I just wanted to get the CL versus CD, go ahead, click 1 to bring up the first graph, right click, current graph, export graph, and then go ahead and save it. I already have everything saved, so I won't do it again, just to save time on my computer, space on my computer. And then now I'm going to move on to the airfoil part. For the airfoil, we do need to do a batch analysis. So I'll go ahead and create another analysis, this time batch. And for the same thing, we're going to go ahead and do, instead of this one set Reynolds number, we're going to go ahead and change it. So we're going to go from 0 to 1,200,000. And at an increment of 50,000. And then the alphas stay the same within our range here. And then the iterations, I like to increase to 1,000 just to help out. And there it goes. So it goes ahead, goes and does this. It does take a little minute as it's going through all the Reynolds numbers and all the alphas there. So all done. And so now we have all this data that the computer can pull from. So we're going to go ahead and start creating our wing. So go ahead over to File, Plane Wing, and then Plane, define a new plane. We're going to call this one AR4 for aspect ratio 4. We're not going to need any fins or any elevators, but we are going to have to define our wing. So here we go. For mine, I went 2. And then the offset is, of course, 0. And 0, 0, 0, 0. The foil type, we're going to follow the Clark Y. And so forth. Everything's there. And then now for the chord length, I actually went ahead and put it down for myself. So chord lengths, we went for aspect ratio. I went for a chord length of 1. And we're going to do 1 on both sides, just so it's a nice straight wing. So straight wing, same chord length for the tip and the root. Offset 0, dihedral 0, and twist 0. Okay, and we're going to save, and therefore it's saved in there. And then we can actually double check, see what it looks like. If we go to plane, if we actually hit this little button here, and we can see we got our nice little wing. Okay, and then from here, it's pretty much the same thing. I'm gonna go ahead and define analysis. We're gonna go ahead and do type 1, and then here a little bit different from the wing, or from the airfoil. Instead of defining which Reynolds number we have to define the free stream velocity to get our desired Reynolds number. So after a bit of calculation, I think I found it to be 15 meters per second. And then you can tell right here, the tip and root are going to be the same since there is this straight wing. So there's no taper ratio. So 1 million and 1 million. So sweet, hit save. And then the same thing as before. Sequence from -5 to 20, an increment of 1. And then go ahead and simulate. I'm going to go check out our polar view. And here we are. So nice, simple. And then for this, we also need the CL versus alpha, which is right here, number 2. And then we need the CL over CD over alpha, so right here, number 4. And then the CL over CD, right here, number 1. Same thing as before to extract the data. If you want all of them, just go ahead when all are shown, right click, current graph, export graph. For example, let's say we just wanted to get the CL over CD. Go ahead, click on 1 since it was the first one, current graph, export graph, and same thing, go ahead and save it. I already have it saved on my computer, so I won't be doing it again. Now for the other wings, you go ahead and pretty much follow the same step. I'll call this one AR8 for aspect ratio 8. And then same thing, define it. So I went ahead and did the same thing where the wingspan is 2. The chord length is 0.5 on both the tip and the root there. Offset 0, dihedral 0, twist 0, and the same Clark Y foil. And all done. Save. And now we need to create another analysis. So same thing, go right ahead. Now, here you can see after some analysis, I went ahead and did 30 since double the aspect ratio, it's going to need to double the velocity to get the same Reynolds number. And right here, you can see Reynolds number million for the tip and the root. So go ahead and save, and we can go ahead and run that. Analysis, please, some points are unconverged. That's okay. At least we got most of them. I think the only one that didn't is the alpha 20, which is fine. We got most of the points. And you can see here in gray is the AR8, aspect ratio 8, Clark White wing. And the same thing for aspect ratio 12. Go ahead, call it AR12. Don't need a fin, don't need elevator. Go ahead, define it. Now this one, I went ahead and changed the actual span just to get a nicer, cleaner aspect ratio. And here the chord is going to be 0.33. And then same thing, 0, 0. And then here you can actually see, oh, sorry, I guess if I'm bring it back to, and then you got aspect ratio 12. Actually, we'll go ahead and keep it there, and we'll change this to 0.5. There you go, nice to keep it. And then there you go, aspect ratio of exactly 12. Go ahead and save that. And okay, same thing as the other two wings, define analysis. And you can see 30 is good enough here. So we'll go ahead and save and then run the analysis. Same thing as before. We just had 1 point, which is totally fine. It's okay. I'm happy with the results. And you can see 1, 2, 3, the 3 wings. And you can go ahead and grab whichever graph you need. Like I said, for the assignment, we do need the CL over CD, CL over alpha, and the CL over CD versus alpha graphs. So these 3 right here. Okay. And then now going on, you can go ahead, once you export these, you can go ahead and start doing a lot more analysis for it. For example, I will go ahead and pull up what I have for it. And we'll go ahead and look at the wings for the CL over CD. So here we are here. And then the zero lift coefficient for each of these is going to be through the CL over CD. So just go ahead and do some analysis here. Just go through, look for the zero, where it's the zero lift. And then find your corresponding CD. And that's that part. Now going on to the 7 degrees question, we can go ahead and change the way we look at it. So as before, this little airplane shows the airplane or the wing in our case. These show the polars, whichever one we need. And then this is going to show the for 1 set point. So for example, if we want to do the aspect ratio 12 wing, we can go ahead and change our alpha here. So here's all of our alphas that we were able to get. So 19 through -5. Question's asking for 7, so go ahead and click 7. So again, you can see right here, alpha 7 degrees. And then the question is asking for the induced drag coefficient and the induced angle of attack. We can go ahead and actually get those graphs. So same thing, right click, current graph, define graph settings, Y span, so the total span of the wing itself. And then here you can click induce drag. Same thing as before, right click, export graph, get the graph data there. Oh, just close out, sorry. So let me just reopen it real quick. So same thing as before, aspect ratio 12, 7 degrees, and this is the induced. If we want to go ahead and change that to find the induced drag coefficient, so the CDI, right click, current graph, graph settings, and then you can go ahead and click whatever variable you want to find. In this case, we want to induce drag. Again, go ahead, double checking alpha is still 7 degrees, and the aspect ratio is 12. We can see right here, aspect ratio 12. And same thing as before, right click, export graph, and you can go ahead and save it. And then after that, it's pretty much just going ahead and plugging and chugging and so forth. Now, for the last part, it's actually asking to find the induced drag coefficient from the CL value, from the lift coefficient value, and at the 7 degrees. And you can actually find the overall average, overall total lift coefficient right here. So CL, and it gives you a value. I'll go ahead and show you for 4, it changes. And then aspect ratio 8, it also changes. So go ahead and take those and then use the equations. I can show which equations I used. Let me just find it real quick. I can't seem to find it, which is fine. But so once you have the CL, you can find the induced angle, which we found earlier. And then from there, you kind of just go ahead and do the equations where it's induced angle equals CL over pi E times aspect ratio, and then the CDI equal to CL squared over pi E times aspect ratio to go ahead and find those. And then for downwash velocity, we know that the induced angle of attack is equal to the negative downwash velocity over the free stream velocity. And then using those in some quick algebra, go ahead and manipulate those to find exactly what you need. And that is how I did the XFLR5 project. Thank you for watching. That's that.